Hi guys, hello everyone, how are you? The continuation of previous video, uh, it is the part of displacement of electrons in the organic molecule. We have seen till now inductive effect and resonance effect. Detailed information we have seen about these two effects, and now third one, electromeric effect and hyperconjugation, we are going to see now. Okay, yes. Electromeric effect. What is actually electromeric effect? We'll go through that. Okay, let us see here. Yes, if you are comfortable with my speed and teaching, you can carry on. But if you are not able to, if you feel that it is very slow, then you can make it fast. Okay, by increasing speed. You can increase speed now, from normal to 1.25, 1.5, 1.75 up to 2 times of speed. You can increase like that. Option will be there. Okay, yes, if you feel that it is slow. To understand everybody, I'm going through this much slowly. Right, now I'm going through here electromeric effect. Okay, let us see here electromeric effect. Third effect here I'm going to see here electromeric effect. Right, now see the complete transfer of the shared pair of electrons. Here, see, the complete transfer takes place. What? Shared pair of electrons. Which electrons? Pi electrons. We can take here through multiple bond. When you take a multiple bond, then pi electrons will be completely shared. Complete shared pair of electrons completely shared. Transferred to the one of the atoms in the presence of attacking reagent. See, important of this effect is only when attacking reagent is there, only this effect takes place. If there is no attacking reagent, then this effect will not take place. Keep that in mind. Okay, in presence of attacking reagent only this effect takes place. You can see here the complete transfer of the complete transfer of shared pair of pi electrons. Shared pair of pi electrons. Shared pair means bond pair. Yes. Shared pair of pi electrons. Pi electrons of a multiple bond. Of a multiple bond to one of the atoms. To one of the atoms in the presence of attacking reagent. In the presence of attacking reagents. It's important. In the presence of attacking reagent, then it is called electromeric effect. Is called electromeric effect. Okay, yes, this is the point you have to keep in mind. Yes, when there is attacking reagent, the completely complete transfer of shared pair of electrons takes place to the one of the atoms, we can say here. Okay, it is a temporary effect. Already we have gone through mesomeric effect is a permanent effect and inductive effect is also permanent effect, but here electromeric effect is temporary effect. Keep that in mind. Electromeric effect is temporary. It is temporary effect. you can say here, keep that in mind. Temporary effect we can say here. Yeah, it is observed by only in organic compounds with multiple bonds, with presence of attacking reagents. Yeah, if there is no attacking reagent, there is no effect, keep that in mind. Okay. Yeah, it comes into play instantaneously. Okay, when the attacking reagent is available, then this effect will be there. If you remove the attacking reagent, then it will move to its original position. Okay. Yes, the addition of acids to alkenes, example here we can see here. Example, you can look at here. Addition of acids to alkenes. Yes, let us see here. Propene molecule, you take CH3 CH, double bond CH2, you can see here. Acid like H plus, you can see here. Any acid you can take which contains H plus. Acid itself, it contains H plus, that's why you take any acid. Then what happens here is it goes and attacks on the acid, you can see here. Then what it gives? It gives the compound CH3 CH. Yeah, since it gets positive charge. It gets which charge? Positive charge, CH3, you can see here. The name of this compound is called propene. Propene, yes, you can see here. Yeah, you can see here. Now see, there it may shift towards this, right? But CH3 group, what you know, it is electron repelling group, means it can repels electrons. That's why the bond is not shifted towards methyl group. The bond is shifted only towards CH2 group. That's why here this is the compound. It can be, this is the reagent. It can see, reagent is acid here. If you remove acid, again it comes back. Okay, if you remove in the presence of reagent, reagent is what here? Acid is the reagent. In the presence of reagent only this effect takes place. If you remove reagent again, then it comes to its original position. Okay, that point you have to keep in mind. Right. Next one, fourth one, hyperconjugation. Let us see here. Fourth one, hyperconjugation. Yeah, let us see here. The delocalization of sigma electrons. See, sigma electrons are there, you can see here. Sigma bond, the electrons which present in sigma bond, those are called the bond pair. Sigma bond pair is called sigma electrons of CH bonded at, yeah, you know, the must and should requirement for this is, the first one is sp2 carbon, which contains sp2 carbon. The molecule should contain sp2 as well as sp3 carbon, and adjacent to the sp2 carbon there must be sp3 carbon should be there. Okay, yes, let us see here. For example, the delocalization of sigma electrons, the delocalization of sigma electrons, that means which present in sigma bond, sigma electrons of CH bond adjacent to pi bond. A pi bond r pi orbital, p orbital is known as or is called hyperconjugation. Hyperconjugation, you can see here. The important point we have to note it here, that CH bond, delocalization of sigma electrons of CH bond adjacent to the pi bond or p orbital. Okay. Yes. Condition for what is the condition for hyperconjugation? Let us see here. I already told sp2 and sp3 how it is. Once again I am repeating. sp2 carbon, sp3 carbon I told, right? Yes, I am repeating once again. Conditions for hyperconjugation. Right, let us see here. There must be alpha CH group. Alpha CH group. What does it mean? We'll go through that. There must be an alpha CH group in bracket we can write sp3 carbon. That CH group, which group? sp3 group, we can say here, adjacent to sp2 hybrid carbon, adjacent to, what is the condition here? Adjacent to sp2 hybrid carbon. Hybrid carbon or other atoms like nitrogen or oxygen. Other atoms like nitrogen, oxygen or oxygen, etc. You can say. This is the most important condition. There must be alpha CH3 CsP3 carbon adjacent to the sp2 carbon. Yes, or this one you have to keep in mind. Okay, let us see the example here. Yes, how it takes place actually, and you see how this effect takes place. It occurs due to overlapping of sigma bonding orbital with the adjacent pi orbital. Yes, it occurs due to overlapping of sigma bonding orbital sigma bonding orbital with sigma bonding orbital present in sp3 carbon, keep that in mind. Yeah, sp3, that is alpha I told, right? Yes, with adjacent pi orbital, adjacent pi orbital or p orbital. P orbital, that is sp2 carbon. It present in pi orbital or p orbital present in what? sp2 carbon. Yeah, here, and keep in mind this effect is also known as, you see, it's very important. This effect is also known as hyperconjugation, is also known as no bond resonance. It is also known as no bond resonance. No bond resonance, we say here. Or we can say that as also Baker-Nathan effect. Baker-Nathan effect. It's very important. They'll ask this in exam. In competitive exam, already they have asked here. Right, keep that in mind. Right, what are the examples? They can participate in hyperconjugation. Alkenes, yeah, I'm writing here examples for that which can participate in hyperconjugation. Examples here: alkenes, you can say here, alkyl carbocations, alkyl free radicals, I already told you, you can go through on previous video, you can watch. Nitro compounds with alpha hydrogen. See, sp3 carbon is called alpha carbon, keep that in mind. Nitro compounds with the hydrogens attached to alpha carbon are called alpha hydrogens, keep that in mind. Yes, nitro compounds with alpha hydrogen. Compounds with alpha hydrogen. Yeah, these are examples for hyperconjugation. Okay, next let us see here some of the how it takes place. Let us see that. For example, if you take here I am showing here CH3, it is CH, I am showing a complete full structure I am writing. CH double bond CH H, you can see. How it takes place, you see, the shifting of, this is sigma bond is participating in hyperconjugation. You can see here the bond is shifted. You can see that is also shifted. Why? Because due to effect of this, because negative charge is coming here, that's why it's move away from this negative charge. Therefore you can show here yeah, let us see. C H H. Since this bond was broken, it can be written as H plus. Why? Because H and H, the negative charge is shifted towards this, to the carbon. That's why the bond is broken. And since it is negative and it is positive, there is a double bond is formed, you can see here. And the next one, what happens here, this bond is shifted towards this, that's why it gets which charge? Negative charge. With lone pair of electrons, there is negative charge on this carbon, and this H is remains same, and this H is also remains same. Okay, yes. Yes, here it is. This carbon is sp2 carbon. This carbon is also sp2 carbon, and this carbon is sp3 carbon. This is also called alpha carbon, and these hydrogens are called as alpha hydrogens. Which hydrogens? These are alpha hydrogens. Keep that in mind. Therefore, sp2 carbon and sp2 pi orbital. Here pi bond, pi bond due to overlapping of pi orbitals. Pi bond is formed due to overlapping of pi orbitals. Therefore, here it is. You can see that pi orbital is there, and this pi orbital and sigma bond overlapping takes place. Okay, you can see here sigma bonding orbital. This is sigma bonding orbital, and pi orbital or p orbital overlapping takes place. We can say here, right? How they can overlap? Let us see here. I'll show you. Okay. Yes. You see. Again, what happens reverse case? It is shifted towards this, and this bond is again shifted towards this. Okay, to and fro, back and forth takes place. Back and forth that process takes place. You can see that. Okay, this is the case. Hyperconjugation in propene. We can say here. This is what here. Hyperconjugation in propene, you can say. Okay, yes. Next, let us see here. When you observe the CC bond length, you can see that in propene are equal to 1.48. It is in between 1.54 and 1.34. Yes. Due to this hyperconjugation, what happens is, actually C single bond C length is 1.54. Keep that in mind. 1.54 picometers, and C double bond C bond length is 1.34 picometers. Okay, bond length. But the CC bond lengths in propene, observed how much, the CC bond lengths both are equal here, and that is 1.48. Actually, see, in case of these are ideals, but in propene, this is propene molecule. You can see here the CC bond lengths are equal, and that is how much? 1.48 picometers. Both bond lengths are same. You can see here 1.48 picometers. It remains same. Okay, it's remains same. We can say here. Yes, you can see that the bond, when you observe in this manner, this, how many number of hyperconjugated structures? How to calculate? How to calculate number of hyperconjugated structures? As the hyperconjugation nature of as the number of hyperconjugated structures increases, stability of the molecule increases. Keep that in mind. as the number of hyperconjugated structures increases, important point, it is examination point of view, they will give you as the number of hyperconjugated structures increases, stability of the molecule increases. Molecule increases, you can see here. See how to find out number of hyperconjugated structures. Stability and number of hyperconjugated directly proportional. If it increases, then see number of hyperconjugation structures increases, stability increases, you can see here. But the point is, you know how to calculate number of hyperconjugated structures. Number of alpha hydrogens, I'll show you here. You know, just take a look. C H H H H H, positive charge. It is ethyl carbocation. What is this? C2H5 plus. Example what I am taking here, C2H5 plus. This is carbocation, ethyl carbocation we call it. Yes. Now when we take this, then when you observe, the bond is shifted here, and you know it can be written as C H H and H plus. Okay, and you know double bond C H H, you can see here. Then what happens next? Further the bond is shifted towards again, because here it is lack of, you know, electrons, that's why you see it becomes now H plus, and there is bond again formed H, double bond is remain same C H H. Then furtherly what happens? C H H, double bond is remain same C. Now this bond is shifted towards this, H is remain same H, now H plus. No, see how many alpha hydrogens are here? Alpha hydrogen, this is called alpha carbon. This is alpha carbon. Number of alpha hydrogens how many? 3 alpha. 1, 2, 3. Totally how many alpha hydrogens? 3 alpha hydrogens are there. You see? Therefore, how many hyperconjugated structures? It is 1, 2, 3, 4. Total hyperconjugated structures how many? 4. Yes. Therefore, the formula for number of alpha hydrogens equal to number of number of hyperconjugated structures. Hyperconjugated structures is equal to number of alpha hydrogens plus 1. This is the formula. Number of alpha hydrogens plus 1. Here number of alpha hydrogens how many? 3. How many number of alpha hydrogens? 1, 2, 3. 3 alpha hydrogens plus 1. Total how many structures? 4 hyperconjugated structures. That's why this is the formula. Number of alpha hydrogens plus 1, that is the number of hyperconjugated structures it gives. As the number of hyperconjugated structures increases, stability increases. Keep that in mind. Okay, yes, this is the point you have to keep in mind. number of hyperconjugated structures equal to number of alpha hydrogens plus 1. We have to keep in mind. Okay, yes, all of you keep that in mind. It's very important to know that. Right. Okay, yeah. Yes, we'll continue this hyperconjugation is there. Still we have to continue this in next video. Okay, thank you very much.